what comes to notion of what is supervised learning then. In supervised learning, there's always this notion, there's a model. A model could be a function, it could be a set of categories, but the idea is you label an existing set of data and try to create the model which describes that behavior. Like there is an output for a certain set of inputs. So you try to create a model which represents that whole set of observations, and then you use that for predicting potential behavior of that on a new data which comes in. So that's why there is always a phase here, which is what is known as training phase. So in the training phase, we take a part of your existing data, we look at the category or target function and try to derive the target model. And when you derive the target model, we also look at how you can use part of data which you set aside to test the effectiveness of your learned model, and that is what is known as test data. So there are several ways by which you can do this training and testing, and then like we discussed, there is no gold standard here saying that 90% is what you should do for training, 10% for test. It could be 80-20, or it could be even things like you can divide the whole sample into 10 very random partitions and then do test and train in each. So there are different ways by which you run your learning algorithm. But key thing is you can never say that there is a globally best possible model which is best for you, because one of the risks we have here, if you have a very good model fitting your current data, that can lead to reduction of prediction capability for future incoming data. So overfitting is something which you should very consciously avoid, which we have to be conscious about. And then where you stop, which is the model you want to project as finally I have done my learning, I want to start putting it into for future prediction, future data. That is entirely dependent upon your interaction with the specific domain expert, and then you come across a conclusion saying that I'm okay with this 98% precision or 90% precision or 80% precision, but I'm able to see that it is getting better in terms of at the compromise accuracy, it's able to get better prediction for the test data. So it is very important for us to understand that machine learning is basically at the heart, it is an optimization problem. Optimization problem means there is some global notion of what is you consider a good fit. It's either in terms of best accuracy or better predictability or some compromise. And then all you may talk in terms of minimization of error or minimization of deviance. And then you try to use that constraint to stop your search for the target function. It's there that machine learning differs from other sciences, where you try to get more precise models, you try to create. So I have a question here. So labels here are created by the domain expert. The domain expert is what is going to give you at the start. In some cases, it may be very evident. Like let's take the example of Twitter feed, right? So it is possible that you may create some standard rule saying that if you're using the don't like, it becomes like negative sentiment. So there we're talking about a model which is basically about categories, the three categories: neutral, positive, or neutral, or we talk about creation of this. But then I'll come back to at the end of today's lecture. I'll give you a very interesting approach where they're saying, I'll tell you that even for creating the labels, sometimes we use a stage of unsupervised learning to somehow create an idea of these are the potential labels, and then use that to feed it to supervised learning. So all I'm saying is there is a huge amount of domain knowledge which is important. I'll give you instance after instance where domain knowledge is important. Let's give you an example. If I'm going through, let's say there are 50 features in data related to, say, an e-commerce company. They're capturing 50 features. And believe me, if you were to run any machine learning algorithm, whether it is SVM, whether it is K-means, doesn't matter. All of them will take orders of magnitude of kind of, what do you say, cost, or in computer science terms, complexity. And you will probably take huge amount of time to converge onto a model with reasonable precision or reasonable convergence. So there you need to take a call by talking to the domain expert. Are all my 40 features important? Are all my 40 variables important? So I may want to concentrate on top 10 or top 6 based on domain variables. So that will bring down your dimensions on which the machine learning algorithm. That's basically the dimensionality reduction we talk about. Why we want to do that is because search space is huge in each of these algorithms, and going through the search space and identifying, running the data iteratively on each of them, then coming to convergence is huge. So like example I gave you yesterday, right? If you're talking about a net, it's today if you do it on a desktop on a kind of a database which is of a reasonable large, you can go into years for computing something. So that's why we need very high performance infrastructure, compute infrastructure like the Hadoop cluster or Spark cluster, or even take it to the hardware level using GPUs from NVIDIA for doing large scale machine learning.